And yeah, I will give you about half an hour to do it. And after that, we will together discuss the answers and also of course the examples. So carefully, of course, your answers. So I hope all of you can access it on the Moodle course. If not, then yeah, I would say just find together in groups of 3 or 2 if you doesn't come out. And start much more this and then half an hour we will discuss this.
Cái là tên mình cái code là cái QR code đó. À vậy. Theo cái
We're gonna collaborate. Thank you. tiếp tục giảm đi thì đăng ký tiếp không.
Okay, so I guess most of you are finished, or is someone still working on anything? Then I guess we could rediscuss the questions in, for one question per group. Yeah, I'm not sure if not like any kind of deterministic direction. Yeah, who wants to start with question number one? Maybe we should start here. So maybe would you want to introduce number one? So, number one, yeah. So exercise number one. Exercise, yeah, question number one of exercise one.
Cho nói ấy trước.
Okay,
Ấy trước này cộng đồng này cộng. Sao không có kêu nó kêu từng nhóm từng bài mỗi nhóm từng bài một con, nhưng mà không chọn nhóm trình bày cho con một chọn rồi con một.
Okay. Which of the statements are correct? So
Do I need to stand up?
what do you ever like? So I can also sit.
Alright, so you
Okay.
think that B and C are correct and A and D are not correct? Because the term big data does not mainly apply to scientific applications. We think that it can apply to many things rather than just scientific applications. And also supercomputers always clusters. We think that is not true. Because there are supercomputers at, I think, like, there are supercomputers that is powerful enough to be just one computer. Because
Yeah, exactly.
yeah. So we decided B and C are correct. That's one.
Yeah, so I would agree. So yeah, I mean A, yeah, as you said, so big data is much broader than scientific applications. So scientific applications are usually more yeah, the high performance computing domain, so where you have like very dedicated hardware for one single purpose which processes very uniform data. And here big data has this, remember this 3 V's, yeah, and so there's these different properties of data, one of which is the variety. So big data is more focused on very heterogeneous data. And yeah, about B, I mean, of course, if you have, I mean, technically, of course, you could set up a cluster software stack for a single computer, but that would not make much sense to call it a cluster. So, of course, in order to have any gain of a cluster or cluster overhead, of course, you have lots of overhead on a cluster. Some software which only is there because you need to make it work somehow. So it would be performant to actually solve a problem on more computers which you can solve on one computer, because you will never reach the scalability of the scale factor of one. It will always be worse than that. So yes, a cluster usually consists of these two nodes. And yeah, about the client-server structure, why would you say? What do you say?
Because in your previous slide, you showed us that there's a kind of structure that there's like a maestro who controls the other workers in a cluster.
Yeah, exactly. So that's true. So that's why they usually do have a client-server structure. So not always, but actually, for example, with Spark, you always have to have a dedicated master node, and then yeah. So this client-server pattern is usually right. But of course, you can have like very often just the case that you have the master node and the slave node and one slave node on the same machine, right? Because the machine can assume both roles. But usually only one machine will assume the master role. Yeah, and the supercomputers are always clusters. Yeah, as you said, not always. I mean, we talked about historically that supercomputers have been single machines and not clusters. I mean, nowadays, usually there are clusters, but not all clusters are supercomputers. And historically, not all supercomputers have been clusters. Okay, yeah, thank you. Number two, what is next in line? So what would say, what is the highest theoretical acceleration according to Arnold's law of 60% of execution time can be parallelized? Your point. Did you get what's wrong with you?
So according to
Yeah. Yeah, I mean, it should be, just a second. It should be 1 divided by 1 minus 0.6. So that would be, correct, it should be like 2.5. So the highest theoretical acceleration, in this case, would be a factor of 2.5. So this is 2.5. Okay, why is there an upper limit for the maximum acceleration achievable controlization? Maybe you can also answer this one. Number 3. Number 3. Yeah. So maybe you can also answer number 3. So why is there an upper limit for the maximum acceleration? So you want to answer this question?
We can only accelerate only parallel path, but there are also parallel paths, so we cannot accelerate that. So there will be a penalty for.
Yeah, exactly. So there's an upper limit because there's always a portion, a share of your execution time which cannot be parallelized. So this is according to Arnold's law. There's an upper limit, and Arnold's law, of course, looks at a fixed problem size. Okay. Number 4. Why is the theoretical speed up according to Arnold's law always smaller than or equal to 1 divided by 1 minus p? With p being the fraction of execution time which benefits from parallelization. Yeah, maybe you can answer that.
well, because we have the formula of the theoretical split, so for calculation, we know that P divided by N, which is the number of processors, will be larger or equal than 0 for all number of processors, larger than 1. So when we add the 1 minus P, which is the zero fraction, so it will be larger than equal than 1 minus P. So when we 1 divided by all of the, then we will know that it will smaller than or equal to 1 divided by 1 minus P.
Yeah, exactly. I mean, if you're inside like 0 for P, you can see that the converges to 1. So it converges to 1. So of course 1 would be the optimum. So you can only get lost in that. Okay, why has parallelization been the why has parallelization been the primary approach for solving hypothesis in the last case? Yeah, exactly. So at one point in time, it was nearly impossible to make CPUs more efficient. So everyone said, okay, let's go for parallelization. Gustafson's law states that a sufficiently large problem can always be parallelized efficiently. This may sound like a contradiction to Ambert's law, but it isn't. Why? Maybe you can answer this.
So basically, the Ambert's law assumes that the problem size is fixed, but Gustafson's law assumes that you can have more CPUs, so you increase the problem size. But if you increase the problem size, the proportion P grows, and that will make the sequential part less significant.
Yeah, exactly. So the one law is looking at the fixed problem size, and the other one at the growing problem size. And of course, if the problem size grows, then this, the performance is ultimately only limited by the parallelization, not by the fixed problem, because it becomes actually at some point it becomes irrelevant. You have a fixed portion which gets smaller to the other side as the data go. So that's why Gustafson's law is actually no contradiction to Ambert's law. Name 2 examples of applications which can be efficiently parallelized according to Gustafson's law. Yeah, maybe you can do it. Good? Are you're not good? Yeah. Okay, but maybe, I mean, if you think of it, so what kind of application would you think right now? What do you mean? What could be application of this? Yeah, I mean, for example, classical movie rendering or so, it could be easily increase the font size, right? Because you have different scenes, so you could assign different scenes to different cores, so it could increase the font size. Of course, only until you have the entire movie and then limited, but until then you could increase the font size. Yeah, basically all kinds of problems. This is actually, I wouldn't say the majority of problems, but maybe it is. But there are many more problems there where this works. Let me see here. Yeah. Also another example would be something like search engines. Yeah. Because the problem size is the number of requests, and the number of requests is so large that this is usually not a limit.
Sir,
Yeah.
can you talk more about question 6?
Yeah.
Can you compare those two ones a bit in details?
You want to have the detail?
I mean, like, I'm not that clear about how they are different and how they are not a contradiction to each other. Can you say it a bit more?
Yeah, just a second. So in Gustafson's law, basic idea is that you have a fixed problem size. So and because your problem size is fixed, you can tell what the fraction of execution time is of the parallel portion of the program. You know that like 10% of the execution time can be attributed to non-parallel stuff. So that's the scenario, right? So you have a problem which is fixed. You cannot increase the problem. So that means that basically if I put more CPUs on the problem, then I would have to subdivide the problem into more partitions. But it doesn't affect this part of the problem which is not parallelizable. That's the problem. We always say the same. And of course, I could like the part which is parallelizable, I could speed up like virtually infinitely, or like many more parallelization. Maybe I could decrease the time right to 0, but we'll still have the entire time of non-parallelizable code. It would still be the very same. It would not change. You cannot, because by definition you cannot change it because it's not parallelizable. So that's basically what he's saying. So if you have a problem of a fixed size, and you know that some part of the problem is not parallelizable, then ultimately you will always be limited by this share of the problem. And with and Gustafson, so this was Anders, and Gustafson said that of course if you have increase the problem size, then you can always find new work for the new CPUs, right? So that's why it isn't limited, and it's also not a contradiction because it's just two different assumptions, right? Is this understandable for you? So, I mean, if you look at Amdahl's law, so this is important. We have a fraction of the execution time that would benefit from the improvement of the resources. This means we also have a fraction which would not benefit from the improvement. This is the part which will actually limit you. You cannot get beyond that. Okay, then two examples of applications that cannot be efficiently parallelized. So these would be like, examples for applications with a fixed problem size. And who was next in mind? You? Or you? Or you were in the same group? Or? Okay. I mean, okay, would you willing to do that? Or the next one? Did you work already on the product? Sorry? so the number 8.
Must be solved in as short time as possible, but we have to
Yeah, but
trade system.
trade system, yeah, exactly. Good example. Yeah. So for example, the trade system, like high frequency trading or something.
Like we have the decision for making the decision making problem in the trade system. That when we have more the data, we would make. We must have a as soon as possible a decision must be have a in very short time as the data is added to the system.
Yes, so this is one example. Also another example which would come to my mind is solving differential equations. This is actually something very important in scientific computing as well. Because, for example, for the physical modeling of the upper atmosphere and weather simulations, you need to solve differential equations. The problem of the numerical solving of differential equations is that you have iterations, and the starting point for the next iteration is the result of the former iteration. So because of this dependency, you cannot parallelize it, yeah? Because well, you always have to have the former result. So it cannot be increased at all. So, and solving differential equations is also something which is essential to many scientific mathematical problems. So there certainly are lots of applications which do not scale this way. So by still we need also very powerful single core systems to solve this kind of problems. Also general database with vertical scaling, right? Because the classic approach of databases, I will also come to this topic later. So there are basically, there's another type of databases, probably some of you already heard of this, it's called NoSQL or NoSQL databases, which are specifically tailored for big data. But the classical approach is the relational database, and this is usually vertical scaling, which means that you have to, in order to make the database more powerful, you need to have a bigger machine. But it's one machine. This can be very difficult to achieve. Yeah, it's very expensive. Of course, you cannot just buy more machines. Okay, number 9. Clusters for big data applications are commonly called horizontal scaling. Okay, that's what I just explained. So, the opposing concept is vertical scaling. So, as I said, so vertical scaling means you have one single machine and you make it bigger. And horizontal scaling is just putting more and more machines to the sides and then connecting them with the network, and then you have a cluster. So if you want to deal with big data, what you do in a cluster, you are doing horizontal scaling. And the main difference is that horizontal scaling scales very well up to very large numbers, because you can add virtually thousands of nodes to a cluster and it's still working efficiently, while you cannot upscale a machine by a factor of 1,000. If you have a very powerful machine, then even upscaling it by a factor of 2 will be a very challenging and expensive task. So horizontal scaling is what actually scales much better than vertical scaling. But still, there are some especially with databases, for example, if you want to buy an Oracle database, which is, by the way, extremely expensive from my point of view, but anyway, if you decide to buy Oracle and Oracle richer, then if you want to have more power, then Oracle will say buy a bigger machine. So by default, it's not possible to scale this up horizontally. Okay. This is some practical calculation. If a CPU has a clock frequency of 20 gigahertz, And the signal travels within the CPU with 2/3 of the speed of light, which is, by the way, roughly accurate. So actually, signal travel in metal is about 2/3 of the speed of light, maybe a little more or less. It's true. How far can the signal travel within one cycle? Did someone do the calculation? Hey, one of you, what did you?
My answer is 1 centimeter.
1 centimeter, exactly. It's exactly 1 centimeter. Yeah. So, I mean, you can calculate. Speed of light is 300,000 kilometers per second. So, this and 20 gigahertz means 20 billion signals per second. So, hertz is the unit of 1 per second. So, if you divide this, then you get, in this case, multiply it with 2/3 and you get 1 centimeter. So yeah, interesting, right? So 1 centimeter is basically the die of a current desktop CPU is about 1 square centimeter. So if you have 20 gigahertz frequency, then the signal cannot really reach every part of the die. Then which of the following statements is true? Yeah, who did that? Wait, one of you did the number 11. And you want to elaborate on this? So which statements are true and which are untrue? B and D is true. And you say A and C is wrong then? Okay. So why is A wrong? Yeah, exactly. So it's important to know that Moore's law is not directly about performance, it's about the number of transistors. Of course, there's a roughly indirect relation to that, but Moore's law basically only says something about the number of transistors in a microchip. And what you do with the transistors also has to do a lot with how well it increases the performance. If you do it not in an efficient way, you may add more transistors without gaining performance, without gaining as much performance as you intended to. So it does not directly say anything about the speed. And also in C, a microchip with twice as much transistors is twice as fast. Not necessarily. So it really depends on how you use the transistors. For example, nowadays some more recent CPUs have added special units for calculation of a certain type. For example, Intel has added parts of the CPU for neural processors, so NPU, so neural processing unit. So this is for AI applications, and unless the software has this certain type of code which can be transformed so that the NPU unit can actually deal with it, then it's not no use. So we have added transistors, but if the software doesn't use this unit, so you don't get that performance. So that's why it really depends on what you do with the transistors. Yeah, D. Sorry. Yeah, exactly. So I mean, you can add features, and these features often consist of adding something which can speed off very special tasks very, very well, but only these very special tasks, not the generic ones. And in contrast to, for example, scaling up the clock cycle will actually increase the generic performance, so everything that happens in CPU. But if you add a neural processing unit and you don't have a task which can fit this neural processing unit, you don't get any increase. So you need special compilers to support this unit, and then create optimized code which actually makes use of this unit. So yeah, exactly. So it really depends on what we do. I mean, it may make sense to have like dedicated units for special problems. So it's called because you have always this trade-off in microprocessor design that if you want to have like a generic performance increase, it's not as efficient as a specialized performance increase in a very special problems. So the most famous example is GPUs, because like in GPUs you have very many parallel units, several thousands of parallel units, which can only perform very specialized tasks. But I mean, in terms of technically speaking, you can always transform hardware to software and software to hardware. And the more generic your CPU becomes, the more you have in software than in hardware. But usually hardware is more performant than software. So that's the reason behind this. So you could always build a special hardware which does something in hardware, which is in other systems implemented in software, and vice versa. It always works. So changing software to hardware makes things faster, and changing hardware to software makes things more generic and more flexible and cheaper. So, okay. Then number 12. What was it that Seymour Cray? Sorry. What was it that Seymour Cray meant with his famous quote, the one with the oxen? Who wants to explain? Maybe he can elaborate on this. Number 12. Okay. So, you already mentioned something. Okay. Did you get to number 12? Okay, so maybe we are running out of time, so I say this. So I mean, I guess it's very obvious. So of course he meant that usually it's more efficient to have very few very powerful processors than very many not so powerful processors. As I said, it was true at this time. And so the last one, why it is difficult to optimize a cluster for high availability, high performance, and high throughput all at the same time. So why maybe you can answer that? What did they say? Number 13? Yeah, so these are actually like not really conflicting goals, but you can only spend money once. Either on very good network components or very powerful CPUs, but not at the same time. So that's usually the reason why clusters are optimized for one of these goals and not all at the same time. Okay, thank you very much. Then, I guess we can meet at like 1:05, so don't want to take away some time from you for your break. So let's meet again at 1:05 here on the continuation.
What about attendance? What about attendance?